I'm Matthew Fairtlough, and I've been commissioned to develop some CDF documents to teach second-year undergraduates at the University of Portsmouth the elements of algorithms on graphs. So, for example, minimum spanning tree and maximum network flow. And it's been a very successful project. I'm going to talk about it.
So yeah, today I want to talk about creating and deploying CDF documents for undergraduate graph theory teaching. And this is a project between myself and Janka Klebikova from Portsmouth University. So I was very happy to get, it was a fairly small, as I thought, application. Janka wanted, she has large classes. Around about 73 students took this part of the module this year. And she found that they didn't really get on with the the traditional mathematical way of presenting algorithms on graphs. So she didn't really know anything about CDF or Wolfram technology, but she'd come across it, and she thought maybe this would be a good tool to help her students learn. So what I'm going to do today is the idea is that there's going to be abstract descriptions of the algorithms. There's going to be some concrete examples, and also the students are going to be able to generate random graphs using the CDF player, and then use these graphs to understand, and there's some feedback mechanism I'll show you shortly to understand how the various algorithms works. So because this is a fairly small project, and it's not like a big grand system I'm going to show you, I'm going to go into some detail about some coding details and the design of the system. So it's a little bit of a tutorial on CDF as well. So apologies if you know all this stuff when you dream about it, but I'm going to go into some detail. Okay, so right, I hope to give a bigger report on the results of using the tool, but the exam's only just been taken and marked, so I can give you some preliminary results, but we haven't got anything definitive yet. Okay, so Janka started off with some PDF files, and she thought this really isn't state-of-the-art. She knew there must be a better way of doing it. So the idea is that the student can control the properties of the generated graphs as well. So they can control the number of vertices, the number of edges, and they can start on simple graphs and then progress to more complex examples. So these are her words, that she felt this was a big step forward from the traditional setting where the students can only use the examples produced by the teacher and can only get help and feedback from the teacher. Okay, so I'm going to show you what the outcome was. We did three algorithms, each in its own CDF document. So the common ones that are taught at this level are Kruskal and Prim. And this algorithm is for finding a minimal spanning tree of a network. I'm going to show you Kruskal's. The Prim's is a similar kind of interface. So as you can see, there's three tabs here: teaching, learning, and help. Help is really just help is not help on the theory. Help is just help on how to actually use the interface, because some of the students have never seen CDF or Wolfram technology before, so they're going to need a little bit of help. So what we did here was just have tooltips, and here I've got sort of dummy controls. If you just click on that, it gives you a tooltip telling you how to use the controls, but they don't otherwise actually do anything. Okay. So in teaching mode, we just look at a fixed example here. So what we have here is a graph, and what it does is it highlights an edge of least weight, and then all you need to do now is the only thing you can do with this tab here is just step forward. So if you step forward, it says, okay, that was the node of least weight, that was the edge of least weight, that was a 3. The next one considered is a 4. and so forth. So it goes through choosing the edge of each of least weight at each point, and then at the end the algorithm terminates. So the interesting thing about, then there were some challenges, the interesting thing about this particular project was that she wasn't really content with this traditional standard graph facilities that you get with the graph package. She wanted to be able to do things like move the edge labels around, and later on we'll see I created a later interface which uses moving nodes as well. So that was an essential feature of the project, and it was quite interesting because that took quite a lot of coding to sort of manage that side of things was actually more difficult than to code up the algorithms, which, you know, a quick look on Wikipedia informed me about how they worked, and it wasn't long to code them, but the most of the time went into the interface. Okay, so the other aspect is you can create a new graph. So you can adjust the number of vertices. Here, of course, the number of edges has to be greater than, well, no more than one less than the number of vertices, because we want to use connected graphs only. And the students can adjust the weight. And clicking on New Graph gives a new graph for them to explore. So this was, again, this was something that Janke felt they needed to have. Yeah. So the other thing that we tried to do was to integrate the theory that the students see with the interface itself. So there was some information here about the theory, which I'm not sure how much the students read. We didn't test that. But the idea was that this should match as far as possible the look and feel of the interface itself, so the students didn't have to translate too much from one notation to another. So this is a formal definition of a network. Many of you will know this very easily. Others may not be so familiar with it. But what I'm going to do is I'm going to show you the next interface, which is for computing the maximum network flow. So a network is an ordinary graph with a source and a sink, and it's a flow is an assignment to every arc such that it's feasible. In other words, the amount of flow carried on an arc is less than the capacity of the arc, or equal to the capacity, and the flow is conserved. In other words, for all internal vertices, the flow in must equal the flow out. So here's an example of a flow. It's not quite fitting on the screen. There we are. So again, a lot of time was spent on deciding. I'm not quite sure I like the eventual colors and style, but this is what the client wanted, and this is what we've got. So there was quite a lot of fiddling around with thickness of borders and so on, which surprised me, as this was my first kind of project of this kind. It surprised me quite how much discussion and work there was involved in just deciding on the look and feel of things. So anyway, that's an example, and you can see that the red ones are saturated. They're already carrying a maximum flow. And the key point for the students to explain, and it took some, I had to look around for some good examples, was in this case, the highlighted. Now, let me show you in a minute, actually. So that's not got the right colors to show you that. Okay. It's going to create a bit more screen space here. Well, that was my idea anyway. Oh, I know why. It's because I've got two tabs here and one's still open. Okay, so the way this works is, the way the algorithm works and the way the students are taught this is that at every stage in the network, either you've got a maximum flow already, or there's a path through the network which augments the flow. So in this case, it's the very first. There's no flow through the network. You can see that all the nodes coming into, all the arcs coming into the terminal node have got zero flow. So the first number is the flow and the second number is the capacity. So this is how it starts out. And the system shows you a flow augmenting path, and all the student has to do is to say what the maximum flow is. So if I open this tab here, so the student is prompted to enter the maximum flow, and it's gone off the rails now, but say if they enter 2, you check the flow along the path, it corrects it for them. It says, no, actually, you can put more through. Yes, sorry.
I have a question to Flo.
Yes?
Is it possible to have self-loops?
Okay, no, that was one of the questions I asked her, and it was a teaching point. Apparently, no, they don't use self-loops in their course, so I haven't actually investigated what happens if you have a self-loop, but it's not... It's possible, yes. But we decided to leave those out because it was a kind of, possibly confusing thing. I mean, the self-loop will just, it doesn't really do anything because it's just going back. It's not going to change the actual, the structure. So we left those out. And also, because you can see everything is a straight line, and I've got an arc label that you can move around, it wouldn't make much sense. It would be more difficult to code it as well. So it was a convenient design decision for me. Okay, yes, so now it highlights the flow that's just been, it highlights the sort of pumping of the data through the flow. So actually the original path has now been augmented, and the first arc is in red to show you that that's at maximum capacity. So, yes, sorry, no, you weren't putting, you were just stretching. So, okay, so if you step through, then it shows you another flow augmenting path. And this was the kind of only algorithmically interesting thing in the example, really, which was that in some cases, you have to undo a flow. And you can see that the arc from A to E is carrying a flow of 8. And yet, on the flow augmenting path, the path goes from S to C to E, and then backwards to A, and then forwards to B, and then down to T. So it's kind of a basic form of backtracking, that we need to undo the flow on the arc from A to E in order to get more flow through the network. So this is probably the trickiest thing for the students to grasp. And what I reckon here, looking at that, is that the maximum flow we can put through this flow augmenting path is 2. So if I check that, yeah. So then it shows the path with the updated flow, and you can see that the arc from A to E has been reduced in the flow it's carrying by 2. And that actually helps us to pump more flow through a different route. Okay, so as I was saying, I think the sort of challenge within a very tight budget and small time frame was to develop a graph system which was interactive and where you could move the nodes around, and you could also move the edges around. And I think it's quite interesting that we made the design decision to spend more time doing that than to implement more functionality. It would have been much faster. I could have done a prototype, I think, with the necessary functionality, but then we wouldn't have had these nice features of the interface. Yes?
Is this a capability of the drawing tool in mathematics?
No, I've had to, no. That's all coded directly in a dynamic module. It would be very nice to have this facility, but as far as I know, it's not in.
Is functionality included in the notebook?
Yes, yeah. So, I mean, I'll show you a little bit about how it works later on. Okay, so as I say, yeah, I'll say a bit more about that later. What we had hoped to do, when you actually go on to the teaching mode and you can design your own graph, here's a slightly bigger one. What we had hoped to do was to oh, I have to edit this. So I've got 3 tabs here. Explore just allows you to go through explore the algorithm by going through steps. So here we did a little bit more in terms of user interaction. It can remember the choices, and it's not really going to be very useful, but the students can go back and review their choices, whether they were right or wrong. And that's another area in which we could improve and extend the package later. So you can either just step through it, because the system computes the series of flow augmenting paths, or the students can actually try to go through step by step and decide what the maximum flow is. As I said, what we had hoped to do was to include the ability to actually define by a series of choices to define the flow augmenting path by starting on an edge and then adding edges till you get to the target. So I mean, and that would be quite feasible to do. It's just we ran out of time and budget to do that. So that taught me something. And let me just show you one other feature that I didn't mention before. That when we're on the teaching mode for the maximal spanning tree, the idea here is that you've got a menu on each edge label, and then you can decide to accept it or reject it. In that case, that was the wrong edge to choose. I should have chosen this one here. If I accept that, it goes green. And in this case, the student can go backwards and forwards and edit their choices. And also, I've added a peak thing, which gives you the whole solution, and a hint step. So all these things obviously could be made more sophisticated, and the system could be made a lot more informative for the students. Okay, so I've got about just over 10 minutes left. So one of the design criteria was that each thing has to be a monolithic. There's 3 things for Prim, for Kruskal, and for network flow, and each interface has to be in its own CDF document, and I've chosen just to have a single thing in each one, because I don't want to have to try and link variables from one dynamic module to another. So each thing is its own separate interface in a single CDF document. But each document itself, as you saw, has to have various components. So I'm going to show you a kind of fairly simple design. This is what I'm trying to build, is a much simpler version of the interface. But as you can see, it's got some controls which are common to everything. So this control for I, for the variable I, will affect the whole system. You don't really need to, what I've done here, I've just chosen to show a panel of data just to show you how the various variables are interacting and changing. So this I is common to every mode here, but if I choose the peach mode, I've got a separate control for peaches, a number of peaches perhaps, and which of course is remembered when you step from one tab to another. So you've got independent controls and independent displays for different sections of the CDF, which, well, I think it proved to be the design that we needed to use for this particular application. So just to show you how we've done it, for those of you who couldn't just do it without thinking, I'm sure that some of you can. So it relies on 3 things. It's a manipulate, it relies on tab view and slide view, and also it relies on controls. So as you can see here, we've got there's one control, which is just a standard control in a manipulate, which controls the main variable I, and then there's 3 other controls, which are basically, it's a slide view. So that's a number of controls within a slide view, which has to be an item, as far as I know. And then you can choose in this slide view which slide you're looking at. So depending on which slide you've chosen, the view will change its value. Here it's got value 2, so it's referring to the Peaches tab. And then the actual control, only the control for the Peaches tab will show on the interface. appearance elements to none means you don't want to see the controls for the slides because you've already got that control on the tabs. Okay, and of course view needs to be dynamic, so it's dynamically updated when changes are made to the interface. Okay. Oh, the only thing is I did find I needed to use, I did a panel on the manipulate, and I set panel to be false because I had a number of nested controls and display areas, and what I didn't want is to have too much screen clutter, because every time you nest one, you get an extra bit of white space. So I chose to use a panel to false, which gives you a kind of manipulate with no borders, and then just to wrap that whole thing in a single panel. I mean, these seem sort of micro issues, but actually, my client was quite particular. She'd say, I need to have this really compact, and I need to have all these features as well. So that was why it was a challenge for me in the time. Okay, so the other thing is, as I was saying, this doesn't have the graph package doesn't have built-in functionality for doing these kind of things. So I built my own sort of custom holder for graphs. And I reused to some degree. I didn't use this very much. In theory, I could reuse the graph package system. So this last clause here allows me to have my own kind of graph within the graph data type, if you like. But that just meant for this code, all this code here is it just strips out my own custom option edge flows, because graph doesn't know about those. So I'll use this for development purposes, but not actually in the final implementation. So that, I had to learn how to do that. And the movable edge labels, this was thanks very much to Stack Exchange. Kuba showed me how he would do this. And so what you do is it's just simply using locators within a dynamic module. This doesn't have manipulate in it, but obviously the eventual one does. And then there's just the code here which uses the locator, which is a function, and so that's the second argument to dynamic. So as you move the locator, it constrains it to move along this particular line here, and also not to move any further. So it was relatively straightforward to extend that to the kind of edge labels I was using, and then later on to actually add movable vertices as well. But quite rightly, I knew I wouldn't have time to discuss that.
And is this dynamic if you move some points?
Yes. So let me show you actually something. I wanted to I'm not going to go through this in any detail because I haven't got too much time now. Yeah, like I said, most of the energy went into designing this. And I just want to show you how I laid out the eventual code. Because it's a monolithic thing, because it was going to be as free CDF, I found that all the definitions and all the variables had to be located within one dynamic module. And that meant quite a large document because there's a lot of different variables. And actually, I ran into trouble, like even in editing. It started to get very slow to edit. So I'd love to find a better workflow there where I can move information in and out of dynamic modules and initialization sections, because I spent a lot of time developing with standalone definitions, but then when I actually had to package it up, they all had to get stuffed into a single dynamic module. So, and I needed some help from the Wolfram help team to do that. So what I've done here is I've just shown you that I've plugged in some sort of dummy symbols, just so this is a kind of form of documentation. You can see I've got a graph in there, but that's just pasted in there. And the interface still works. It's just, in this case, it's just a fixed thing, and I can't actually move it around. So, but the interesting thing here I noticed is you've got to be a bit careful. You asked if they're dynamic. If I move this, oh, I can't. Hang on, wait a minute. I should be able to move that. I can't. Okay, well, that's all right then. I think it's because, yeah, I could move that. And now I find if I go back to my code, that point is going to have moved. Okay. Well, anyway, this actually was something I discovered yesterday. I didn't really intend to demonstrate, but this is a kind of form of self-modifying code I produced here that when I actually evaluate it, it actually goes back and edits the code that I've written. So you've got to be a bit careful with it. I suppose that just illustrates that manipulate and dynamic are very powerful things. Okay, so I don't have much time to talk about algorithmics. There's built-in algorithms for computing the maximum flow through a network. They work in the graph package. But because I wanted to do it step by step and show the students all the details of the algorithm, it wasn't possible just to use that functionality. So I wrote this thing. I've called it shy because it was a bit shy in revealing its secrets to me, because this was just slightly tricky in terms of coding. It was the most interesting algorithm thing. All it's simply doing is it's finding all the paths through a network from one start node to a finish node. So there's nothing very, very dramatic to that. But I needed to make sure that that it was sound anyway. So that's just a bit of code that shows you how to do that. I won't go into details because I'm running out of time. Okay, so I only have time to report very briefly on the results of the teaching. She had 73 students. The course was a course in mathematical foundations of computing and functional programming, although that wasn't exhibited here in this talk. And graph theory is just one component. So Janke said the results are slightly better. They were better by up to 5%, 40%, okay. Well, it goes up to 45, which is not great, but the feedback from the tutorial was good. They liked the chance to play with the software. She's not sure how much they used it outside the tutorials. So I did promise to talk about deployment, and basically it was just a downloadable CDF file because we couldn't integrate it with Moodle, and it just wasn't worth the trouble to do so. I think it would be nice if we were able to deliver it over the web, but I don't think this code will work with with the new online Mathematica tools, so we won't be doing that. Okay. Yeah, hopefully in future years you'll use them, and perhaps what we'd really like is to get a teaching grant to develop this further, or some kind of resources so that we could sort of roll this out a bit more to more students, and hopefully they'll find it useful. I had a slide, which you can see if you download the talk later, on how we can improve this and extend this. And I think it does need refactoring because it's a very monolithic thing. It would be very good to make it more modular. Okay, thank you very much.